Okay, we're going to start into a section on connected particles. So we've got two objects which are linked, and there's two ways they link them. One is by lighting extensible string, and that means that as long as the particles are moving and keeping the string taut, so moving, one's trying to move away from the other. They probably won't, because they're lighting extensible. Both particles, when they move together, they will move with the same acceleration, the same velocity, and the force is the net force that comes from this. So if we've got resistance here in 1, the force that's left over from the acceleration and this tension will lead to some force inside that string, helping retard this. And that string will also be applying a force on the second object. Now this situation in the middle is something called Newton's third law. The third law states that each force has an equal and opposite force on anything that is connected, and connected without any further forces happening. So each of these can have their own resistance. We've got the thrust being applied, and we have an overall acceleration for the two particles, and they can be completely different masses. That would allow us to solve these formulas, and we'll solve a problem like this in a minute. The counter position, though, with a light inextensible string is if one particle is moving towards the other, there is no tension here. There's no newtons happening in here. There's nothing actually trying to put work on this one. So what can happen is that you might be moving together, and then they say, right, we're going to start slowing this one up. What happens? And they will possibly come together, but you have to calculate where there's no tension. So this is the position where one particle is trying to move away from the other, and then this one is where one particle is either trying to move either towards it, or one is moving. Well, yeah, this one would be moving towards that one, and that would lead to no force in this connection. Okay, so that's one important thing about strings. Strings can only apply what's called a tensile force. In a rod, what can happen is we've got the same thing. If they're both moving together that way, they will both move with that acceleration and that velocity, and they will have a connected force here, a tensile force, and that will be transferred from one to another. This one, where it starts trying to push, what will happen is everything goes into the other way around. This tries to push, so this is pushing on the rod, and the rod pushes back on the first particle. The force being transferred, these two parts on a rod are the same. So these forces I'm showing are the same in each place. So this rod would wind up pushing on that one to make that one move, and with it being a rod, they're unlikely to ever give you something which is going to buckle or change. So we could wind up with an acceleration going this way, and they will accelerate together as well, go in the opposite direction. And that's a light rod. The light means there's no mass. Where's my pen gone? There we go. So light means no mass. So it doesn't actually affect the system itself. It doesn't apply any forces itself. The inextensible means that when you put something under tension, the force is immediately transferred. Transfers. Okay, so under tension, an inextensible string acts like a rod. Under compression, it will have nothing. So if the two things are trying to move together, there is nothing. That's two key points on these shapes. So I'm just going to set up the question. Okay, so this is an example. It's in the book, and what we're talking about is two particles that are connected with a light inextensible string. So we've got a let's draw a quick diagram of what's happening. We've got two particles, one with a mass of 5 kilograms, one with a mass of, I could make it bigger so they've got bigger mass. We're going to say that one particle is, because I want to move right, I've read the question, P is pulled with a force of 40 newtons. So there's a thrust this way, 40 newtons. Q, and we've got to assume that they are being pulled to cause the string to be tense. So the force, as this pulls this way, Newton's third law says it will experience some tension coming back. And Q will feel the same tension going forward. We have resistance force of 10 newtons on the first particle, and that's what this respectively means. So first of all, it's on a rough plane, so there is friction, and it's telling us exactly what the friction is in each case. So we put those in. When you see the word respectively, it says in the same order. 6 newtons. We've got a mass of 3 kilograms. We've got a mass of 5 kilograms in that one. And both particles are going to move together because they're on an inextensible string. So they must move in the same way. So they both experience the same acceleration. Now, because we know that it's moving horizontally, not vertical, I'm not going to fill in the extra bits that they do in the book, which are the vertical forces. In many situations you would do. So actually I will put them in, but I'll put them in quite lightly. So we've actually got a mass here. The weight of Q is 3G, and the reaction force is 3G. The two are equal. And that's on Q. The weight of P is 5G, and the reaction at P must be equal because there's no motion vertically. Okay. So what we can do first of all is, as they're moving together, we can actually treat this as one system. For part A, they want to find the overall acceleration. So in part A, find the acceleration. And as they move together, we're going to treat them as one particle. So we've got a single mass. The mass is 8 kilograms, being pulled one way with 40 newtons, being pulled with a resistance of 2 newtons forces together. So it's got 10 plus 6 newtons. And the net result of those forces is an acceleration. So because of this light extensible string, the two particles are effectively glued together as one. So we're going to put in our motion. And that's MA is equal to the forces. So let's choose this as a positive direction. And the acceleration direction is positive. So the positive force is the thrust, which is 40 newtons. And subtract from that the resistance or friction, which goes in the opposite direction of 16 newtons. So we've got, that's what we're describing up here. It's not too clear in here what they're saying about this. The resistance and the motion, we've got to assume the motion is going in the same direction as the acceleration. Because they don't actually mention that this is from rest. So we've got our 8 kilograms is equal to 16, so 24 newtons, so A is 3 meters per second squared. The second part we've got to work out is now what is the tension in the string. So part B, tension in the string. And what we can do is we consider each particle. And we can choose either particle to resolve all the forces acting on that particle only. So we could do it with P, we could do it with Q. And so let's consider only Q. I'll show you, it should work out as well for P. So if we consider Q, we've got, my pen's just locked out, we've got 3 kilograms with a thrust coming from the tension. We've got 6 newtons pulling it backwards, and it's accelerating, we now know, at 3 meters per second. So I'm going to just scroll down so I can put the two calculations side by side. So I'm going to make the motion equation. So we've got motion on the left. You don't have to write this motion and label it. I'm doing it to be clear. Motion is MA, so that's 3 times 3. Let's put the units in so we know it's mass. So we've got 3 kilograms times 3 meters per second squared. We've got the thrust, and we're going to keep this in the positive direction going right. So we've got the tension pulling us forward. That's the thing we want to work out. And pulling us back is 6 newtons of friction. Negative because it's going the opposite direction to our positive motion. So we get 9 minus 6 equals T. 9 plus 6 equals T. So it's 15 newtons. Just to check, we could also consider BE, which is again 5 kilograms being held back by 10 newtons and pulled back by our tension. We've got our thrust forward now of 40 newtons. The vertical forces aren't needed in this diagram. So I do motion, and again this is accelerating at 3 meters per second squared. So I've now got 5 times 3, that's my equation of motion, is equal to 40 newtons in the direction of travel, minus 10 newtons, and minus my tension. So if I rearrange this, I've got T equals 40 minus 10 minus 15. 40 minus 10. Sorry, my arithmetic was just messing up with me. 10 minus 10, 30 minus 15 is 15 newtons. So we get the same solution. They go on and ask you things about what are the assumptions. Well, in extensible, the masses will move as the same acceleration and the same velocities. Light, the tension will be the same both ends because there's no force or weight in the string itself to change that tension. So that's the first type of problem.